Hello folks. Okay, this is another video about the regular direct comparison test. So I'm just gonna write it as comparison test. So I'm gonna put some examples about comparison test, and this is, sometimes they just say it's the direct comparison test, or it's just simply, you can just say comparison test. So here's the first example. So the question is this: the sum starts from 1 up to infinity, and it says 3 to the n divided by 2 plus 5 to the n. So the idea is this: if your terms of the series are positive up to some point, it may start by, for example, the second term, third term, like 100th term, it doesn't matter. If it just becomes all positive, you can compare it with something that you already know, whether it's convergent or divergent. And if it's less than something convergent, then this should be convergent. If it's larger than something divergent, then it should be divergent. So, and of course, I can just say this is not the only test. If you want to use, for example, limit comparison test for a problem like this, it will work. It will work, and you need to evaluate some limits, and that's all. But here you need to do the comparison carefully. It should be, for example, if you say this is convergent, it should be less than a convergent series. And if you want to say this is divergent, then this should be larger than in divergent series. So I'm going to just show you two examples. On this one, so you can see on this one you have a 2 added to here. So if I get, you see this is always positive. We know that this is always positive. And if I get 3 to the n divided by 2 plus 5 to the n, look, there's a plus 2 added to the denominator. And if you add a positive number to the denominator, you're obviously making the fractions smaller if you add a positive number to the denominator. So and be careful, it's all positive. So this will be really less than, and just say 3 to the n divided by 5 to the n. It's a sequence. For all n larger than 1, this is true. This is of course, I can just say this is positive. It's greater than or equal or greater. And you see the series of this sequence is just geometric, and I know what happens to, I know the behavior of this one. If I take this one as a sum of the series, it's just sum is just n starts from 1 up to infinity. You can just see that's just 3 over 5 to the power n. And if you look at the common ratio, which is r, you can just see that's 3 over 5. And absolute value of r is less than 1, so that implies that this series is just really, this series is convergent. So you see this is kind of your an, this is another, this is like your bn. An is less than bn, and the sum of bn's is convergent. So when this is convergent, you see the comparison test says if it's less than a convergent series, then your original series must be convergent. So I can just say by comparison test, I just use the abbreviation this to be just CT. By comparison test, given series is convergent. So this is really just one way. So you make your original series less than a geometric series. It's kind of like acting similar, but they have the same behavior. Now this is the first example. Now if we just go to the next example, this will be involving some p series, but it's again, I want to say this again, for this example, you may really use the limit comparison test. If you want to try, you can, but here we go. 2n plus 1 divided by 3 times n to the power 3 halves minus 2. So when then n starts by 1 and goes up to infinity. So of course the question is just convergent or it's divergent. Just figured it out. So folks, again, as I said, if you want to use the limit comparison test, you can really use it, but in the problem, if it's specified, like if it says, okay, prove that this is convergent or divergent by using the comparison test, then you have to use that one. So in that case, you really have to know what the comparison test is. So now you see n starts by 1, and once n starts by 1, this n to the 3 halves will increase, and just you're only subtracting 2, and there's a 3 as a coefficient, and this is positive integer, so this will be always positive. Even if it's negative for some certain terms, that's still fine, but it shouldn't be alternating. Just be careful with that. So in this case, it's just all positive. And you see, now here, it's kind of like you're adding 1 to the top and subtracting a 2. You see, I mean, you can really start by this way. Try to get rid of those constants. And I have 3 to the power 3 and to the power 3 halves minus 2. Look, if you subtract 2 from the denominator, you see, of course, you're making your fraction for the positive terms, you're making it larger because you're subtracting from the denominator. So I can definitely say this is larger than 2n plus 1 divided by 3n to the power 3 halves, because I subtracted 2. And then next you added a 1 to the numerator. So see, I first get rid of this negative 2. And then next I'm looking at this plus 1. So if I add a plus 1 to the top, I'm making the fraction larger. So this is again larger than 2n over 3n to the power 3 halves. But, well, this is really interesting because the constant, you can really take the constant out 2 over 3. And I have n and n to the 3 halves will cancel. So this one will cancel by that. I mean, you can just see that that's basically n times n to the power negative 3 halves. And this is like 1. So that will be n to the power negative 1 half. If you want to compute this directly. So this is like 1 over square root of n. So 2/3, that has no effect on the sum. I mean, on the behavior, of course. If the 1 over square root of n is just a series of the sequence is just divergent, 2/3 will just make it also divergent. Maybe a little bit goes to infinity, maybe slower, but still it goes to infinity. And if you look at this one, sum 1 over square root of n, this is a p series with p equals 1 over 2. This is square root of n, and p is less than 1 makes this series, so that implies this series, of course, talking about this one, this series is divergent. So you know the p series, if p is less than 1, it's divergent, then it's less than or equal 1, then it's divergent. Let me just put that sign. If it's greater than 1, then it's convergent. So here it's divergent. And our series, given series, if you look this, an is larger than bn. And of course this one is divergent. So that implies, since that's divergent, that implies that, I mean, I can really write that 2 over 3 sum of 1 over square root of n is also divergent. So that multiplying by 2/3 will not change the behavior. Still it will be divergent. And you see this all positive numbers, it diverges to infinity. So multiplying 2/3 will not change it. So this is divergent, and we go back to our problem. So our series, our sequence, I mean the terms are larger than the terms of this sequence, and this series is just divergent. So our first series must be divergent as well, since it's larger than that one. Like, think of this way, you have a sum which is larger than infinity by comparison, so that has to diverge to infinity as well. So we just write by comparison test the first series, the given series. The given series is divergent as well. So as you see, I mean, you just try to get rid of the constants if it's possible, but sometimes it may not be possible. For example, if that was a plus 2, then that will be a problem, because adding a plus 2 makes it smaller, whereas adding a plus 1 to the top makes it larger, so it really does not fit to this problem. If there was a +2, then you will need to use a limit comparison test. But it just works for this problem, so it's really a nice one. And hope this will help you to, hope these two examples will help you to understand how we apply the comparison test. Thanks for watching. Bye.